Okay, so today we're going to talk about volumes by slicing. What we are going to be given is a region, a two-dimensional region, and they're going to tell you that the region is the base for some sort of shape, okay? And that shape is going to create a three-dimensional object. So here, we have the region of y equals x squared and x equals 2 in the x-axis. And sitting in that region are rectangles. So it creates this three-dimensional shape. Okay? Here we have triangles sitting in our region. Okay? Basically, if we were to slice this three-dimensional figure, the slices of bread would look like triangles. Okay? Here we have this region, and it has like a semicircle shape. So if we slice it like bread, we're going to have semicircle slices of bread. Okay? And as we get, like, depending on where we are in the region, will depend on how big the diameter of that semicircle is. So as we get to these smaller parts, we have smaller and smaller semicircles. Okay? Over here again, we have like rectangles. All right, so we have this region, and we have these slices of some shape sitting there, creating together a three-dimensional figure. Okay, if you want to think of a loaf of bread would be a rectangular region, where sitting in that rectangular region would be squares, and then if we slice it up, we have slices of bread. Okay, that's essentially what's happening. Now, in order to be able to determine the volume of these, we're going to take the area of each slice times the thickness of that slice, which is going to be either dx or dy, depending on our rectangles, and then add them together. How do we add infinitely small things together? Using a what? Okay, let's get a little more calculus than that. If we wanted an infinite number of rectangles added together to determine area, we figured out we could just use even better than that. We could use an integral, right? Right? We did Riemann sums, but then we got to integrals. Okay, so now we have infinitely many areas with thickness dx or dy that we want to add together. Okay, here is how we're going to find the volume of those. We're going to take the integral of the region of the area times the thickness. Okay. Okay, the book has some pretty good graphics for you to look at, and when you do your homework tonight, they're going to have a graphic for each problem that you do. So that should help your visualization. Okay, I know it's weird to see a two-dimensional region and imagine things popping out of it, but we're going to do our best. Okay. So we're going to go through, I think, 4 examples today. All right. Let's go ahead and look at this one. So I want the volume of the solid whose base is bounded by the graphs y equals x plus 1 and y equals x squared minus 1. And our cross sections are perpendicular to the x-axis, and they're going to be squares. Write down whatever information that you need to. Okay, so we have y equals x squared minus 1 is a parabola. And then y equals x plus 1 is this line. And so we're talking about this region right here. Okay. What's happening is we have bases perpendicular to the x-axis. So I'm going to draw in my rectangle perpendicular to the x-axis, which means dx. And all of these are squares. Okay. So basically, no matter what rectangle we would draw, it's going to create a square popping out at you from your page. Okay. Okay, so this is our base right here. How do we figure out how long that base is? How long is that rectangle that we drew? Oh, you're getting too complicated. How do we know how long that rectangle is? Or any rectangle that we draw in here? What do we do in area to figure out how tall a rectangle is? Well, the function, right? The top of our rectangle sits at x plus 1 minus the bottom of our rectangle sits at x squared minus 1. Too hard. Okay? Any rectangle that we draw in that region is going to have length top minus bottom. Okay? So the base of each figure that we would draw here is x plus 1 minus x squared plus 1. Right, if we distribute that negative. So let's go ahead and write it as x minus x squared plus 2. Okay, that's how long that rectangle is that we drew. Now, that's the base for our cross section. And in this case, our cross section is a square. How do you find the area of a square? The area of a square is just side times side, right? So the area of a square is side squared. Well, this is the base of that square. So if this has length x minus x squared plus 2, then so does the height of the square. So our area is side squared. So our volume is the integral of the area times the thickness. So what we need is the area times the thickness. That's creating our third dimension of volume. Last thing we need are the limits of integration. Okay, where does this region begin and end? So it starts over here. What coordinate is that? Okay, so x equals -1, right? And then we have to figure out this coordinate right there. You can use your graph or you can use algebra. What do you want to do? What? Sammy says it's 2, 3. Does that satisfy both equations? It satisfies the line, satisfies the parabola. So this is the coordinate 2, 3, which means our limits of integration are -2 to 1. -1 to 2. Said that completely backwards. Okay. The integral, which means we're adding up area times thickness. So volume. What? Too easy? Okay. All right, you want to calculate that in your calculator for me? This is not one I would make you do by hand. That's a little bit more algebra than I would prefer you to have to do.
So why do we have to multiply this by 5?
Because we're not talking about a cylinder, right? For the disc washer method, we were talking about cylinders or discs, and so we were talking about circular regions. It's 8.1? Is it a fraction? Can it go to a fraction?
81 over 10.
Do you agree with Jake? It really was 8.1. Sorry, I thought there was one, but okay. Questions on that first example? Now we have a solid whose base is bounded by y equals x and y equals x squared. That's a nice region, right? With cross sections perpendicular to the y-axis, and they are rectangles whose height is twice the base. Okay, so write down what you need to. Y equals x and y equals x squared. What a great region, right? Nice and simple. Okay. Now, our cross sections are perpendicular to the y-axis, which means we have rectangles drawn in here with thickness dy. Okay. So let's talk about how long each of those bases would be. Any rectangle with thickness dy that we draw in that region has a base of what length? Jake, what are you guys talking about? And what is your possible answer?
Maybe x squared minus x, but maybe it has to be rearranged to be x equals.
Okay, let's answer Jake's question. Does it have to be rearranged to x equals?
Yes.
Yes. Since we're going to have to integrate with respect to y, we are going to need to change, this is x equals y, and we're going to have to change this to x equals positive radical y. Okay? So now that we've rearranged those, Jake, what would those bases be? Radical y minus y, right? Minus left. Okay? So each base, that is like the one noise I cannot see.
Joe Conant says.
No. False. Okay. Now, let's talk about the area of each of these slices. Okay? If we talk about the area of each slice, we are talking about the area of a rectangle. How do you find the area of a rectangle? Width times length. They're describing it as height and base. So can I write base times height? Doesn't matter? No. Okay. But since they use base and height, I'm going to use base and height. Okay? Now, our base is radical y minus y. Our height is twice the base. So here's our base, and then our height is double that. So could we really just write this as 2 times radical y minus y, the quantity squared? Are you okay with that? Okay, so then our volume is the integral. It looks like our region goes from 0 to 1 of area times thickness. So we're adding up all of these slices of bread that are infinitely small, infinitely thick. Right? Not a piece of bread you want to put in a toaster. With your calculator, find it for me. It is possible that it's not going to be a rational number. Is it rational?
Well, I'm not sure if I picked the right number, so I just multiply it that way.
I think you look like you have a number.
0.06.
That seems very small, doesn't it? Huh?
However, it should be small.
It should be small, right? Think about how thin that region is, right? So those rectangles are going to be pretty small, right? And that was an irrational number to answer correct, right? Okay. All right. Let's have some fun. Okay, the region R is the base of a solid. For this solid, each cross-section is perpendicular to the x-axis, that's important, is a semicircle whose diameter runs from the graph y equals radical x to the graph of y equals e to the negative x. Find the volume of this solid. Draw with your finger. What does y equals radical x look like? Shooting star? Draw with your finger. What does the graph of e to the negative x look like?
Influx here. Gonna be reverse of e to the x, which is a growth. Now it's gonna be a decay from there.
It is a decay intersecting at 1. And so the region that we're talking about, and it would probably say, I probably should have put in there, we need to be in the first quadrant. Okay. Well, but there's nothing, this doesn't keep going, so I guess that doesn't make sense. Okay, there's our region. All right. They're saying our base is perpendicular to the x-axis. And we have semicircles. Okay, so let's just first talk about the base. The base, how do we find its length? Okay, furthest one minus the closer one. So in this case, e to the negative x minus radical x. Okay? Now, some of you are going to be able to think about the base and not have to write that step down, and that's okay. But I do want you to think about the area before putting it into an integral. Okay? So the area, how do we find the area of a semicircle? 1/2 pi r squared. When we're talking about these semicircles, what does e to the x minus radical x represent on our semicircle? That is the diameter of the semicircle. So if we're talking about area, then our radius is going to have to be half of the diameter. Okay. Now, here's what I need from you. I need to know the x-coordinate of this intersection. Can you please find it for me? Connor, do you have it?
I got 0.426.
Connor got 0.426. Do we agree?
Yep.
Okay. So there's our limits of integration. Then we need our area times the thickness to get that third dimension for volume. And then that integral is going to sum up those infinitely thin semicircles to get our volume. Okay, if you calculate it for me, let me know what it is. Joe, do you have it? Cleaning your Jake has 0.035. Can you confirm Jake's 0.035? I'm seeing some head nods. Okay. Once again, that is a small number, but that is a pretty small region. So those semicircles are going to be very small. All right, this is what I'd like you to do. I'm going to put a problem up here. You and your pod are going to come up with the setup for the problem. Okay? Look at that, I even gave you the graph. You and your pod are coming up with the setup of this problem. Okay, so look at this.
Wait, was that
so if you want that to be divided by 2, minus radical. So like
you guys aren't putting the 6 in there, right?
Okay, so this, we open the bracket to be divided by 5. And then we're going to close the bracket.
So first, right there.
And then close the bracket.
But however, we're not subtracting it by anything.
So then X.
Yeah, the base is, no. The base, but however, is 0. You're subtracting it from 1, so it's just. So you're going from the x and y squared. Because the y equals 6 is just going to help.
Y over 2 squared and y is 0.
So just y squared over 4 you need.
Y squared over 4.
Oh, I
want
Yeah.
So that's
okay, so area equals.
but we need. Alright, so that's the length of its base. So that times
So B, so
and we're just multiplying it.
Oh, I know what we did.
Those two are the same, so you get 3 squared over 4 squared.
The height is the base times 3.
So y over 2 declines squared times 3 times. Y
Just go by PI.
You're not going to do that, are you?
I mean, I'm going to need it for college anyway.
Well, I would simplify it. I mean, you can simplify it to y squared over, or y is equal to 4 squared times 3.
Okay. So let me go over this and then.
I just don't want to have 2 squares. Well, you have to have times 3.
based off of 3.
Pod number 5, what is the base length? Yeah.
Just y squared over 4.
Y squared over 4? Okay. The area, pod 2. What's the area for each of those cross sections?
3b squared.
3b squared, so 3b squared. Okay. So pod 1, your integral. Okay, and then
the area. And then.
there it is. Make sure your limits are 0 to 6. We have to take the y values because we're integrating with respect to y. Do you have a question? Pod 5, do you have a question? No? Okay. So your homework is 2 problems. Whoops. Your homework is 2 problems that have multiple parts.